Hello, everyone. So we're going to start chapter 6. And chapter 6 is about relations. So we're going to do a little unit on relations and functions. Functions in chapter 7. And we're going to kind of revisit what we know about relations and functions from algebra, but also introduce some terminology that's sort of more advanced, kind of fits in with some of the stuff that we've been doing with logic and proofs. Let's look at some definitions, okay? So definition of a relation, right? Says, let's see, if we have A and B are sets, then a relation from A into B is any subset of the Cartesian product A cross B. Okay, so basically we have a set for our input and a set for our output, and we make pairs of numbers, x, y values as we know them, that express the relation between those two sets. Okay, so there are a few ways to express relations. So sometimes you can express relations as coordinate points, just in a list like this. You can represent relations graphically. You can express relations with a formula. So those are kind of things that we're familiar with, or with tables. Okay, so we're probably going to look at a couple of ways that you haven't used so much in algebra, but they're going to be useful in this unit right here. Okay, so let's look at this example 1. We have A is set that contains elements 0, 1, 2, and B is the set that contains elements A, B. And we formed the relation from A to B, so this is kind of a description of that relation. Like 0 goes with A, 0 goes with B, 1 goes with A, and 2 goes with B. So this is a relation from the first set to another set, okay? As I said, sort of list of coordinate points works for representing a relation. Also graphically, what we mean by graphically here, we're going to basically list the first elements of the first set, 0, 1, 2, like this on one side. So those are elements of set A, and the elements of set B are A and B. And basically we can use arrows to show the relationship between the two sets. Okay, so arrows going from set A to set B, we're pointing towards set B. So because 0 goes to A, we're going to have an arrow going this way. 0 goes to B, we have an arrow. 1 goes to A, and 2 goes to B. Okay, so these are graph arrow diagram like this. Okay, so sort of when we're gonna talk about graphs, mostly for the rest of the semester, it has to do more with these diagrams, arrow diagrams, rather than what we traditionally know as graphs in algebra. Okay. And again, we might talk about real numbers, but mostly we focus on the sets of integers to be our inputs and our outputs. Okay, so I said that we can also express a relation with tables. Okay, so kind of the traditional tables. We have our inputs and our outputs. So x and y values, we can sort of list them side by side. So 0 goes with A, 0 goes with B, 1 goes with A, 2 goes with B. All right. There's another type of table that's sort of useful. Let's say we call this relation R. So this is relation R right here. You'll see that relations can be given capital letters and lowercase letters. They're fairly interchangeable. And here I'm going to have AB, and here I'm going to have 0, 1, 2. So we're making a grid more than a table. All right, so basically we're going to put an X if those are connected, and leave it blank if they're not connected. So 0 and A, there's a connection between them. 0 and B, there's a connection. 1 and A, there's a connection. And 2 and B, there's a connection. So this is like a little grid representation of that relation. Okay, Cool. So let's go and do learn a little bit more and do some examples. All right, so next definition, we call a relation from a set A onto itself, we call it a relation on A. Okay, so often the input is the same, the input set is the same as the output set. So we say that a certain relation is a relation on a set A. Okay, so we again are familiar with this in terms of we have functions where the domain and the range are both the real number system, all the real numbers, and then we say that's a relation or a function on the real numbers. Okay. All right. So next definition, we're going to look at the definition of divides again, which is we saw in the last chapter. So if a and b are integers with a is not 0, we say that a divides b, denoted by this bar. A divides b if and only if there exists an integer k such that a times k equals b. All right, so divides means that it divides evenly into, so b is an integer times k. Okay, so we're going to see the divides by operation with quite a few relations in this chapter and probably the next one. All right, so let's example 2 kind of relates to that. Let's say that A is the set of elements 1, 2, 3, 4. Which order pairs are in the relation that says R is the set of order pairs where A divides B. Okay, there should be a little squiggle here. Right, so it's like because I'm given only one set, basically this set A, it's a relation on A, is the input and also the output. Okay, so we want to look at figuring out what elements are in R. So we're going to list them. Okay, so the elements that are in R is sort of with using these these elements as the input and the output are all the ordered pairs where the first number divides into the second one. Okay, so if we just sort of look at the first one divides into 1, 1 divides into 2, 1 divides into 3, and 1 divides into 4. So all those are elements of the relationship. Now let's kind of go with the 2. So 2 divides itself. 2 does not divide 3, but 2 divides 4. If we look at 3, 3 only divides itself. And if we look at 4, 4 divides 4. Okay, so with this set of integers, 1, 2, 3, 4 being the input set, the output set, those are all the elements that we get that fulfills that description. All right, cool. All right, let's look at this example. So in this example, we're going to see some kind of definitions of relations that we're going to use quite a bit in this chapter. We'll kind of see this again when we talk about properties of relations. So we're going to get familiar with them. So here I listed R1 through R6. There are kind of a few different sort of definitions of a relation and the sort of set builder notation. And let's see which of these relations contain these pairs listed right here. Okay, so let's look at each relation in turn. Okay, so R1 says is the pairs of numbers A, B for which A is less than or equal to B. Okay, so let's see which one of these fit into that definition. So 1, 1 certainly fits in. I'm just basically trying to see which ones are in there. 1, 2 fits that description. 2, 1 does not. And 1, negative 1 does not. And 2, 2 fits that description. Okay, so those order pairs are in there. All right, let's look at the second relation. So second relation is defined as ordered pairs for which A is strictly bigger than B. And we see that the ordered pairs above here that fulfill that, that rule are 2, 1 and 1, negative 1. Okay. Third relation, set of points where a is equal to b or a is equal to negative b. And so basically the elements are either the same or opposites of each other. Would be 1, 1, 1, negative 1, and 2, 2. Okay? All right. R4 is the set of coordinate points where a equal to b. So this fits with 1, 1, and 2, 2. R5, set of coordinate points where a equals b plus 1, or a has to be 1 more than b. So that one is just the 2, 1, right? It's the only one that fits with that rule. And the last set is the set of points where a plus b is less than or equal to 3. And that fits with 1, 1, with 1, 2, with 2, 1, with 1 and negative 1, but not with 2, 2. Okay? All right, so as I said, we're going to revisit these relations again when we talk about properties of relations. Basically these are defined on the set of integers. So we're just kind of seeing which of these specified coordinate points fit in these relations. But these relations are formed by an infinite number of pairings because they are defined on all the integers. But it's helpful to kind of look at a snapshot and see what kind of coordinate points each of these relations contain. All right, here's another definition. This definition defines the composition of relations. So we're going to look at a composition of two relations, although this can be extended to many more. So if R is a relation from set A to set B, and S is a relation from set B to set C, kind of the important part is that these match, because like a chain rule kind of thing. The output of the R relation needs to kind of be the input of the S relation, and then the composition can happen. And the composition of R with S is written RS, right? So this is the set of pairs of the form A comma C that are in the Cartesian product of set A and set C, where A comma C is in RS if and only if there exists a B in set B such that AB is an R and BC is an S. Okay, so so that's the composition of two relations. So the notation we're going to see is R composed with S like this. This is the same thing as S of R or S of Rx if you're kind of thinking in terms of functions. Okay, so we're not talking about functions yet. We're just talking about general relations. But I sort of to kind of relate with what we know from algebra, this is basically the same as what you've seen with composition of functions. Okay, and interchangeably we also use like capital letters for the names of relations. So don't be surprised if I kind of switch from lowercase or uppercase. They're kind of the same thing, right? So let's look at example 4. So what is the composite or composition of the relation R and S, where R is the relation from 1, 2, 3 to 1, 2, 3, 4, with R defined here, and S is the relation from 1, 2, 3, 4 to 0, 1, 2, with the relation defined here. So first of all, you kind of basically need to double check that the set, like the output set of relation R, matches with the input set of relation S, and that way you can compose them. All right. So you can sort of find RS just kind of by looking at the sets. All right, but I want to draw a little diagram here that just to help us visualize. So the input for R is 1, 2, 3. Right, and the output for R is 1, 2, 3, 4. So let's look at the R relation right here. So we're looking at this coordinate point. It says that 1 goes to 1 and 1 goes to 4. Make a little arrow diagram here. 2 goes to 3 and 3 goes to 1 and 3 goes to 4. Okay, so this helps us visualize R. All right, so now let's go to the relation S. So the relation S goes from 1, 2, 3, 4. So these are the inputs here to 0, 1, 2. So the outputs are 0, 1, and 2. Right, so let's look at the S relation. Let's draw some arrow diagrams here. So S says that 1 goes to 0, and 2 goes to 0, and 3 goes to 1, and 3 goes to 2, and 4 goes to 1. Okay, so when I'm doing the composition of this, I'm basically going from the input 1, 2, 3 to the output 0, 1, 2, sort of connecting these with that set 1, 2, 3, 4. Okay, so let's say if I want to find all the ones that start with a 1. Okay, so you can just follow the arrows. So 1 is going to go to 1, which ends up at 0. So 1, 0 is in a point in our composite. Okay, I also see that from the R diagram, 1 goes to 4 and 4 goes to 1. So that means that 1 eventually ends up at 1. Okay. And again, you can do it by reading the sets too. So you go 1 goes to 1. And if we read the S diagram here, let me just make a little bit, I'm erasing everything. All right, let's see. All right, so yeah, 1 goes to 1 and 1 goes to 0. This is this. 1 goes to 4 and 4 goes to 1. That means that 1 goes to 1. Okay, so you can do it directly from the sets, or you can do it with the arrow diagrams. I like the arrows because it just helps visualize. All right, now let's move on to the 2. So here 2 goes to 3 and 3 goes to 1. So 2 ends up at 1. 2 goes to 3. I see there's another path. 3 goes to 2. So 2 ends up at 2. All right. So we're done with the 2s. Now 3 goes to 1, which ends up at 0. And that's good. And 3 goes to 4, which ends up at 1. Okay. All right, so this is basically, I took into account like all the possible inputs 1, 2, 3, and followed the arrow to see where we end up with the outputs in the green set right there. So this is the results of the composition of RNS. Okay, let's look at one more example in this section. So we have R is defined to be this relation right here. And I want to find the powers of Rn. So power, like R squared, means R composed with itself. And R cubed is going to be R squared composed with itself. So, and because we have the sort of same input and output, so 1, 2, 3, 4, 1, 2, 3, 4, sort of, I think we need to basically take the input and the output to be the same sets in order to be able to do the composition. Okay, so let's look at what the result would be. So let's have our input numbers here, 1, 2, 3, 4, and our outputs 1, 2, 3, 4. All right, and the relation R is going to have the arrows going from 1 to 1, 2 to 1, 3 to 2, 4 to 3. Okay, so if I want to compose it with itself, okay, then we're going to do 1, 2, 3, 4 like this. So like these become my inputs and they go to the outputs. So let's draw the arrows. So 1 goes to 1, 2 goes to 1, 3 goes to 2, 4 goes to 3. So we're applying the R relation again. Okay, so R squared, let's see, so if we start at 1, we end up at 1. If we start at 2, we end at 1. If we start at 3, we end at 1. And if we start at 4, we end at 2. Okay, so this is our R squared. All right, let's actually see if I can move this. Move it over here. Yeah, that's not working. Okay, it's fine there. All right, let's see. So let's do it again. I want to find R cubed, so we're going to continue. So 1, 2, 3, 4. So apply R again to the outputs. So 1 goes with 1, 2 goes with 1, 3 goes to 2, 4 goes to 3. Okay, so let's see what R cubed is. So R cubed, basically, we're start at the beginning and we want to see where we end up. So 1 ends up at 1. 2, following the arrows, ends up at 1. 3 ends up at 1. And 4 ends up at 1. Okay. All right. Let's see if we can spot a pattern. Okay, so let's do one more. And I think that will be apparent. So let's do R to the 4. So again, 1 goes with 1, 2 goes with 1, 3 goes to 2, 4 goes to 3. And R to the 4, we can see that 1 goes to 1, 2 goes to 1, 3 goes to 1, 4 goes to 1. All right. Okay, so yeah, so we're to get the relation, the first numbers here are the input set, so you want to follow the arrows to the output set and see where they go. Okay, and you can see that for any relation, any power, this is going to be true. Whatever the input is, you're going to always end up with an output of 1. Okay, so that's the sort of formula for the composite and a composite of this relation. Okay, so this is the end of this section. We're going to go on to the next section and find out more definition and properties with relations. So see you there.